Hey everyone, and welcome back. Before we begin here today, please make sure that you like and subscribe because it really does help out our channel and it also helps us reach others in need of assistance with these topics. So in today's video, we are going to be going over 3D components and resultants, and this will be our first video on this subject in statics. And what we have to do here is we have to determine the magnitude and the coordinate direction angles of the resultant force for the system shown here. So we have two forces in the system, and of course you can see it's in 3D because now we have an X, Y, and a Z axis. So anytime you have a problem that is in 3D and it's asking for find the resultant force and basically its location, meaning the coordinate direction angles, the first step is always to break up your forces into the X, Y, and Z directions. Then you're going to sum those forces in each of those directions, and then you're going to find the resultant from that. So first step we need to do is that we need to look at each individual force and break it up into its X, Y, and Z directional components. So let's start with F1, which is right here, down here at the bottom, which is 450 newtons. Now, looking at the directional arrow here and what is given with our arrow for F1, we have a 3, 4, 5 triangle along the Z and Y plane. Well, this means that the Fx component for F1 will be 0 because it doesn't have any directional force along the x-axis. It is strictly only in the y and z. There is no percentage of F1 that is in the x direction. So that's a pretty easy one right off the start. Now, let's go ahead and find our Fy component for F1. How much of it is in the y direction along the y-axis here? Now, F1 will be located along the positive y here because this arrow is down and to the right along the z y-axis. And to the right along here will be positive, noted here. Anytime you have 3D, where the label is, that is where your positive directions will be, or you can set them as that, and it makes life so much easier for you. So looking at Fy, what it will be our magnitude of F1. And since we have this little directional triangle here, we're going to use that to ratio how much goes into the y direction. So whenever you're dealing with these little triangles, and these little triangles really only work on a 2D plane, in this case, the y and z axis, you're going to take the dimension of that triangle that is parallel to the direction you're looking at. Well, we're looking at the y here, which is somewhat horizontal. And the 3 right here on this triangle is horizontal, so that would be our numerator. And then our denominator will be the hypotenuse of that right triangle, which will be 5. So plugging in for F1, we have the 450 newtons here times 3/5, and that gives us a total of 270 newtons in the y direction for F1. All right, now let's repeat the process for the very last one, which is a z, and that's the way I write z's with a little slash through it, just so you denote it differently from 2. So whenever you see this written like this is just how I write z's. It's called an engineering z. Because let's face it, a lot of people's handwriting is hard to read, so that just helps it out. So once again, it's going to be your main force, which is F1. And then once again, we're going to use that little dimension triangle. Same idea, we're going to use the dimension of the triangle that is parallel to the direction we're looking at. Well, Z is purely up and down. It's vertical. The 4 is vertical. So we're going to use that one. And then once again, always over the hypotenuse there, which is 5. So let's plug in 450 for F1. And that gives us, or multiplied times 4/5. So 450 times that gives us 360 newtons. Now, what you have to pay attention here is the direction of F1. If we said the upward direction of Z is positive, that means that this axis down here is negative for Z. Well, F1 is going in the downward direction. So this 360 actually will be negative. It will not be positive. Positive would mean that we would have an arrow upwards. So its component mapped onto the Z would be in the upward direction. Well, that is not the case here. We are downwards. So we are minus 360. Just something to look at when you are breaking up these forces along a 3D axis. If you have any questions about the 3, 4, and 5 triangles, please look at the 2D systems or the 2D videos for components and results that we have on this channel. Better explanation there, because usually you will not find this on a 3D problem, because most 3D problems will have forces in all directions, which is the way F2 is. So now that we have F1 broken up into the X, Y, and Z axis, we're going to repeat that process for F2. So let's go ahead and let's find our x component of F2. How much is in the x-axis here? Well, no matter what you're doing, it will always be the magnitude of the force you're breaking up. In this case, we're looking at F2. Now, since we have angles from each axis, we are going to use directional cosines for each of these angles here. So we would take F2 and it would be times the cosine of the angle that is off the x-axis. And depending on how you actually represent that, nomenclature can be different. We're just going to call it theta x for the angle off the x-axis. So plugging in for F2, we have 525 newtons times the cosine of the angle off of the x-axis to the force we're looking at, which is 45 degrees. And that gives us a total Fx of 371.23 newtons. Now, keep in mind, using these directional cosines, it is always best to use the angle from the positive axis direction. So this is off of the positive x. If it was off the negative x, we would have an angle going back here towards the negative x direction. All right, that's why our answer came out to be positive. So moving on to Fy, same idea. We're going to use the magnitude of F2, the force we are looking at. And we're going to use cosine of theta y, which is the angle off the y. Well, what's my angle off of my positive y direction? Well, that would be 120 degrees. Well, that means that we are past 90, so we would be in the negative y direction, which is located in this direction over here. So we expect this answer to be a negative value for Fy because the cosine of an angle larger than 90, between 180 and 90, is going to be negative. So we plug in 525 newtons, cosine of our angle of theta y, which is 120 degrees off the positive y-axis. And we end up with a minus 262.5 newtons, which is what we thought we would get would be a negative value because it's in the negative y direction. A lot of little checks that you can do along the way here to make sure you're in the right process or in the ballpark. So Fz, how much do we have in the z-axis, which we kind of scroll down, but that's our positive z-axis there. Same idea, once again, the force we're looking at, its magnitude, times cosine of theta z, which is the angle off the positive z-axis, which in this case we are measuring at 60 here. So just plug and chug, and we have 525 newtons. Cosine of that angle off the positive z, which is 60 degrees. And we end up with 262.5 newtons. All right, so these are my components for each force. So this tells me what I have in the x, y, and z for each force that we have on the system. Now, if we had more forces, we would just repeat this process until we have done every single force. So if you have 100 forces, which, oh, that's a large problem, well, you go through all 100 forces exactly the same as this procedure. All right, so now that is usually where you differ the most on these problems. The process that comes next will be pretty much the same all the way through here. So now what we're going to do is we are going to sum forces in each direction, just sum our components that we have. So for F1, we have 0. For F2, we have 300, a positive 371.3 or 23 newtons, which gives us, well, hopefully you can do the math on that, 371.23 newtons. And then let's just repeat that process for the y, summing in the y direction. Well, for F1, we have a positive 270. And Fy for F2, we have a minus 262.5. So we would have positive 270 from F1, minus off the 262.5 newtons for F2. And that gives us a positive 7.5 newtons for Fy. All right, and then lastly, we do summing of forces in the z direction. We're going to have a minus 360 plus 262.5. So minus 360 from F1 plus 262.5 for F2. And that tallies up to give us a negative 97.5 newtons. All right, now that I have summed my forces in each directions, I do not need my information for F1 or F2 anymore. Because what I have found here, these are the components in the x, y, and z direction for my resultant force. So how do I get to my resultant force? Well, it is very similar to using the Pythagorean theorem, but now we're in a 3D model here. So my resultant force will be the total summation of my x's squared plus the total summation of my y's squared plus the total summation of my z's squared, and then all of that square rooted. So we have all those answers. Here's the summation of my fx, fy, and fz. So let's go ahead and plug these in, and we would have 371.23 newtons squared, plus the fy, which is 7.5 newtons squared, plus the fz, which is minus 97.5 squared. And don't forget the square root. Very easy to forget that square root there for your resultant force. And this resultant force pops out to be 383.9 newtons. And that is our magnitude of our resultant. Now, whenever a problem asks for magnitude, that is the answer for the magnitude. If it is just asking for some other force like a Cartesian vector notation, we will do problems like that. But whenever it's asking for magnitude, you want it as a single value in newtons. You don't want anything with an I, J, K format if it just says magnitude. So that is our answer for our resultant magnitude. Now, we also have to locate this resultant with its coordinate direction angles. And what that means is that we need to find the resultant force from the x, y, and z axis. Well, how do we do that? Well, it's very similar to what we just did for F2, but now instead of F2, I have R. And for instance, instead of Fx, I have the summation of Fx. So it's kind of like working in reverse, not really, but the same principle that you got F2's components, but in the backwards direction. So from the x-axis, we'll do that one first, commonly referred to as the angle of alpha. You can also call it theta x, just depends on who's doing the problem, what your professor really cares about and what they like. If they're super particular, it doesn't really matter as long as you have the same nomenclature and you know what that nomenclature represents. So in order to get that angle alpha, it would be cosine of alpha is equal to the summation of x over your resultant r. So if you rearrange, we would have alpha is equal to the cosine inverse of the summation of x, which is 371.23 newtons, divided by my resultant, which is 383.9 newtons. And my alpha comes out to be 14.8 degrees. Please make sure that your calculators are in degrees and not radians, because we're looking for directional angles here, and we're going to give those in degrees. So that's all for my x. And now we're just going to repeat that process for the y and z. And it's going to be the same basic layout. The y-axis is commonly referred to as the beta angle here. So we're going to have cosine of beta is equal to the summation of fy over r. So beta is equal to the cosine inverse of the summation of fy over r. So if we scroll back up here, we would have 7.5 over 383.9. So 7.5 over 383.9 newtons. And my beta angle will pop out to be 88.9 degrees. All right, so now we just have one more directional angle to find, and then we are done here. So off the z-axis, commonly referred to as gamma. Well, just following the same pattern that we've had before here, the cosine of gamma would be the summation of the z forces over r. And what is my summation of my z's? Well, it's minus 97.5. Now, when you have a negative, it really doesn't matter inside the resultant magnitude determination here because you're squaring it. Squaring a negative, it's a positive. But that negative does matter a whole lot when you're looking at the angle off the axis. So my gamma angle would be cosine inverse of my summation of z's, which is minus 97.5 over my resultant force of 383.9 newtons. And once we calculate this out, we get 104.7 degrees, which makes sense because anytime you're doing cosines and you have negative values involved, you're going to have angles between 90 and 180 degrees on these axes here in this 3D problem. So those are my directional angles. Now you can leave them as this answer, in my opinion, that's fine. Well, you have to determine what your professor actually wants, but we have the magnitude resultant, angle off the X of 14.8, angle off the Y, 88.9 degrees, and the angle off of the Z-axis of 104.7. Keep in mind, those are off the positive axis directions. So if we wanted to actually draw it out like this is what we would be representing with our resultant force down here, angle alpha off the X, angle beta off the Y, and our angle gamma off the Z direction. And that would be your complete answer for this problem. So hope you enjoyed this video and I hope you found it helpful. And if you want to see more problem solved this Friday, please check out the other videos on our channel. Also, if you haven't done so already, please like this video, leave a positive comment below, and subscribe to the channel because all of that does help us out greatly. Thank you for watching, and I hope you have a fantastic day.